All right, good morning, everybody. So welcome back to PreCalc. We're going to finish up doing some modeling with exponential functions today. I'm going to apologize for the two rants I'm going to have beforehand, so we can make sure that take that with all salt, and then we'll go from here. Okay. So I want to start with that. I don't want to start with that. Okay. So this is taken from a quiz I gave before, quiz 5. Okay, and here we have a detective is called to the scene of a crime where a dead body has been found. She arrives at 10 p.m. and immediately records the temperature of the body to be 80 degrees Fahrenheit. 1 hour into her investigation, she measures the temperature of the body again to be 76 degrees Fahrenheit. She notes that the thermostat is programmed to be a constant 68 degrees Fahrenheit. And assuming the victim's body temperature was normal, 98.6, which is not really normal anymore, but that's a different topic. Prior to death, when did the death occur? And then here we have T of T, T of little, big T of little t. Okay, just wait, when you get to differential equations, we'll have big T, little t, and then we don't have enough t, so we go to tau for the Greek T to make sure that we have all the t's. But temperature of time t is equal to the environmental temperature. That's going to be our programmed thermostat, plus your initial temperature, starting temperature, minus the environmental, e to the kt, and we're going to have to figure this out. Okay. So this was a fairly common problem. Okay, but notice, like, I don't expect you to memorize a formula like this. Like, I will give it to you and I will spell it out to you because I know this is a difficult formula, and I know seeing something like this on a test is a little traumatic, which is why all of the little pieces here are all given to you in in how you want to do this. All right, so let's go ahead and start doing a couple of things here. Okay, so the first thing I'm going to do is I'm going to write down the pieces here. So we have T of T is equal to T sub E, that's the environmental temperature, plus T sub 0 minus T of E, E to the KT. So just as a note for your professional development, what you want to do like later in your careers, anytime somebody hands you a giant formula like this, before you start plugging in numbers, write down the formula with just the letters, and then you can start filling in the specifics. You can start filling in these specifics, because the worst thing you want to do is you want to confuse one of these things. All right, I guarantee you, I've done it. I've done it in engineering. It doesn't matter who you are; they will laugh at you. Okay, they will have a very good time doing it, but you really don't want to be that person who mixed up the formula, because they will never, ever let you forget it. Okay. The other thing you want to do for your professional stuff is see if you can't find reasonable numbers for this, and see if the answer you get is something that's reasonable, because that's another thing that they will never let you live down. And even if that happens, like it happens to everybody. Okay, so we're just going to abbreviate this to T. I guess we could put a little T in here, but we're just going to abbreviate. That's the temperature. Okay. T sub E, right? That's our environmental temperature. That's our 68 degrees. Okay, actually, I'm not even going to put the units in because we're not really going to need them. Okay. Plus, what's the initial temperature? Well, assuming it was a living body before he got murdered, right? 98.6, and then temperature of the environment, 68. Okay. E. Sorry, my cat is she's got a bit of a heart condition, and we don't have she can't be anesthetized, so we can't get her neutered. So she's an indoor kitty, and getting pregnant would be a bad thing for her, and going into heat is something we have to tolerate. Being neutered would also be a bad thing for her. Okay, so that's what we know. And now we have to figure out, okay, well, almost every one of these problems is like a 1-2 punch kind of a thing. There's always a part A, there's always a part B. Even though they don't spell it out for you, there's always a part A, there's always a part B. So here, right, here they give us something, right? They say, well, 1 hour, right, somewhere in here, 1 hour into our investigation, we find the temperature to be, right, 76 degrees. We don't know how long she's dead, though. We don't know how long this person is dead. So actually, I'm going to change this T sub 0. I'm going to change this T sub 0 to be 80, because once the clock starts at 0, the temperature is 80. When we advance the clock 1 hour, right, which is what we're going to do here, we're going to go ahead and say 1, and we're going to have a different value here. Okay, so we're going to have, right, in 1 hour, 76 degrees is equal to 68 plus 80 minus 68, okay, e to the, right, and I don't know the k, but I do know that t is 1, right, it's been 1 hour. So the reason I changed that to 80 is because when my time was equal to 0, my temperature was equal to 80, right? So T sub 0 is going to be 80. So notice in this case, right, when we end up solving this thing at the end, we are going to have a negative time, but let's presume that, this person was murdered before 10 p.m., which is when we set the 0. So the negative numbers is just going to be like, if it was -1, it would be 9 p.m. Okay. So in this case, we are going to set time. We are going to allow time to be a negative number because it just means time before 10. Okay. And then here, okay, we have to solve for k. All right. So let's go ahead and do that. So the first thing we're going to do is we're going to subtract 68 from both sides. Right. So 76 minus 68, I think that's just going to give us 8. Okay. So we have 8, and then 80 minus 68, what's that going to give us? That's going to give us 12, isn't it? 12e to the k. Now, you don't have to type in the 1 if you don't want to, okay, but we're going to go ahead and figure that out. So we have divided by 12, so we're going to have 8/12, which is the same thing, right, as 2/3, I believe. 2 times 4, yeah, 2/3 is equal to e to the k. So at this point, we have to say, well, the natural log of 2/3 is equal to the natural log of e to the k. K is equal to the natural log of 2/3. All right, so that's one thing we can figure out. Okay, alternatively, like you could just note that k is equal to the natural log of 2/3, and like maybe put a k sub 1 or a k sub 0 here. So you would just be able to know to put this back in later. Okay, that's usually what I tell my students to do is, just note that you now, k0 equals this thing. And that way, when we have to solve for it later, you can just substitute back in natural log of 2/3 rather than putting this number in, right? So natural log, and you don't know how many decimal places, right? 2/3. Not too many, right? Because we measured the temperatures in whole degrees. Okay. So instead of carrying this around, usually I suggest 4, right? Instead of carrying this around, we could just say, well, I'll go calculate natural log of 2/3 when I need it. Okay. All right. So we know where k is equal to this. By the way, this is the FBI does research into this. Okay. Figure out what the heat constants are for bodies in certain environments. They put them in trunks, cars, and things. Okay. So now we have to change things. Okay. We don't know. Oh yes, we do. So now we're going to figure this out. We're going to say, yeah, I wonder if this will work. Let's try it. Okay. So let's see what happens if I put a 98.6 in for my temperature equals, and then we'll just let everything else kind of be the same here. So we're going to say this is 68 plus, okay, 80 minus 68, e to the k, I'm going to put a k sub 0 here, t, and now we're going to try to solve for t. See if that works. Okay, so we're going to go ahead and say this is 98.6 minus 68. All right, so that's just going to be, looks like a 30.6 here, right? Is equal to, and 80 minus 68, that was still 12. E to the what? To the negative, to the k, to the kt. Okay, let's go ahead and divide both sides here by 12. All right. So we've got, let's see, we've got 30.6 divided by 12. Oh my goodness, it's almost like this problem came out of a textbook or was absolutely designed for somebody to solve it really easy because all the numbers happen to work out. This is going to be a number that's positive, okay? So we're going to have k, which we know, right? We know that k times e to the e, which is 1. We'll try to solve for the k, equals natural log 2.55. And then what we're going to do is we're just going to say t is equal to the natural log of 2.55 divided by k. And k was times the natural log of, what was that, 2/3? And I can just figure that out. Okay, so we're going to say this is natural log of 2.55 divided by the natural log of 2/3. Okay, and we got t was equal to negative 2.3. Okay. So interpreting what this means in the problem, right? That this person was killed about not quite 2.5, but 2 and a little bit hours ago. So if they found the body at 10 p.m., 2 hours before that's going to be 8 p.m., but it's actually going to go back in time a little bit more than that, so somewhere between 7:30 and 8 p.m. All right, so get your list of witnesses from there, and then we can go from that. Okay, so that is how you do a problem like that. Okay. I'll just tell you off right off the bat. Like I remember what I was thinking when I was picking this problem. Notice all the numbers are real easy to deal with. This makes a really good final exam kind of a problem. Okay, because you don't have to hassle with a lot of numbers. You don't have to hassle with a lot of decimal places. That's what takes all the time. So this is a good problem for that. Okay. All right. Let's see here. We have quiz 5. I was going to use quiz 6 for this one. All right. All right. So conversely, this would be a terrible final exam problem. Okay, because there's a lot that I look at this one and there's a lot to read. Okay. So on the morning of October 15th, 1927, it's a dim autumn day. A group of men, I like this one, it's very poetic, foregathered at the Rosedale Cemetery in New Jersey and picked their way along the headstones to the grave of one Amelia Molly Maggia. Okay, she was an employee of the United States Radium Corporation, USRC. She had died 5 years earlier. Okay, so we're putting her time of death as 1922. Okay, so I'm just going to say time of death here. The date of death, right, is 1922. Okay. All right. Died 5 years earlier at the age of 24. To the dismay of her friends and family, the cause of death had been recorded as syphilis. But when her coffin was exhumed, its lid levered open, Molly's corpse was still seen to be aglow with a soft luminescence. Everybody knew what that meant. And what that means is that she died of radium poisoning. And because the factory didn't want to pay damages, they just spread the rumor that she was a whore and died of syphilis. So that's how they treated her. And actually, if you look at, I think the Radium Girls was a movie, or at least it was a couple of years ago, maybe before your time. But that's how they treated most of the women. They would, they were giving them radium paint to paint clocks and dials for use in airplanes for nighttime raids during the wars. And to paint the dials, they would get these crappy brushes. They would dip them in the paint, but the brushes wouldn't hold a point. So between putting the paint on the letter, the paint on the numbers, they would put them in their mouths and make a point so they could dip them back into the paint. And that's what they would do every day. And at the time that they got hired, people thought radium was good for you. And recently, after a couple of years of this, decided that radium was not good for you. But there was mostly women were employed to do this kind of work because it was artistic. So that's what they advertised. But because they were women, they would also they would terribly mistreat them. So when they found out it was dangerous, they didn't tell the factory workers. They didn't tell the clock painters it was dangerous. They just said, just keep doing, just keep dipping the brush in your mouth. That's fine. And I mean, dozens of girls suffered horribly under this. And there was a very long court case for them to get any amount of compensation out of them, and it really wasn't enough. I mean, it was, they would pay them like $1,000. I'm like, okay, yeah, I know you've had to, the dentist, the doctors, everybody we went to had no idea what was going on. It was just, it was an agonizing death for a lot of these women. So, there, that's rant one. Okay. All right. Let's see. If Molly had 10 milligrams of radium, that's actually too much. If Molly had 10 milligrams of radium when she died in 1922, how much does her body have today? Notice I can use this question every year. We know that the half-life of radium is 1,600 years. Okay. So since this is a half-life problem, right, we're going to start with our Q is equal to Q sub 0, e to the KT. Okay. And we know that there was 10, really probably should have been micrograms. Okay, oops, that's all, I don't want that. I don't know how much she has today, right? The initial amount was 10, E. I don't know what K is, okay, but we have a time, right? We have 1,600 years. In 1,600 years, how much of this radium is going to be left? Half of it. No matter how much I started with, the answer is half of it. Well, half of 10 is 5. Okay, and we're going to use this to generate our K. Okay, so divide by 10, so we get half is equal to e to the 1,600 K. We have to solve for K. It's in the exponent position. The way we get it down is take natural log, so we're going to take natural log of both sides. This exponent part, this comes down on a baseline. That's exactly what we want. Okay, natural log of 1/2 over here. Okay, and now we know that K is equal to natural log of 1/2 divided by 1,600. Okay, and I'm just going to put this as a K sub R for radium. Okay, the Curies, right? Marie Curie, they invented this. They found this stuff. They had this radioactive pitch, and when they, like tar, when they took out the uranium, or when they took out the uranium rather, the pitch actually got more radioactive. It was actually more dangerous when they took uranium out, and they found that the stuff was in it was radium. You still can't touch her lab books. They're behind a leaded window in the museum, I believe in France. Okay, it is 2021, and Maggie died in 1922. That's 99 years, isn't it? Wow. Okay, so that was in 99 years. So how much is left? Q is equal to 10 e to the, I'll say k sub r times 99. Okay, and all we have to do is figure this out. Okay, that's all we have to do. So we have to do 10. If you ever have to read an older book that talks about e's, this is how they're going to represent it. So it's all on one line. Exponent, and then we're going to have natural log of a half over 1600 times 99. Okay, so in our calculators, because that's what we have to do here, is we're going to take 10 times the exponent, e to the, and then we're going to type in natural log of 0.5. Don't forget these, that you need that parentheses there. Okay, divided by 1600 times 99. If you put parentheses around the 0.5, natural log 0.5 over 1600, that'll be just fine. Okay, so if you want to separate that out a little bit, that's fine. So our current amount here is 9.5 milligrams, 9.6 milligrams of radium still remains. So that's, yeah. So there we go. Okay. So there we go. That's this one. Okay, that's a terrible final exam problem because there's a lot to sort through. The problem itself isn't really that bad, right? So this is a good test question because you have a little bit more time, but you can see I've asked this question several times, right? Yes, I am a little fascinated with radium. Sorry. So that's what it's. See, they said, this is great. This will be a cancer cure. Yeah, I suppose. If you're dead, I guess you don't have to worry about the cancer. But yeah, they would give it to people and they would drink it. They would paint stuff with it. They would let people not bathe in it, but like, bask in its glow. And it was pretty bad stuff. Okay. All right. We'll do another one of these in just a minute. Okay, we're gonna look at something else for a second here. Rant number 2. Sorry. So we talked a little bit about the the logistic curve. This thing is A1 plus B e to the kt. Okay, that's the population curve. A is max population. Okay. So we did one problem that talked about computer viruses, but this also works for like, human diseases too. And, once you know where this is, then you can kind of calculate like what's going to be the end. And with Corona, what you're looking for in a country or a region is this kind of curve, because that's going to be, that you've got it contained and the infection should be tapering off. The timeline for this is really long. So what I did here, just to give you, I hate this kind of graph. Okay, this distorts almost everything. It's very hard for people to actually look at this graph and know what's going on. So I really hate these. But for the coronavirus, this is the cumulative weekly count that we have. Okay, so this is not daily. This is just the amount that we have here. So you see Europe, right? I've got a little bit more hope for Europe. United States, we're starting to level off, so that's good. right? You can see it's a much, you know, well, I wouldn't say nicer, but it's at least it at this point a lot earlier. Okay, but that's how you're going to know, right, that the things are starting to, you know, things are starting to calm down. It's not a panic anymore when we're doing this. Okay, so United States, we're getting there. India's getting there. Brazil, I don't have a lot of hope for Brazil. They are still in the beginning part of that curve. I hope that I hope this curves over and it changes. But Brazil is going to be in a world of hurt. You know, France. A lot of these, when I was looking at the individual countries, it was see, this is not good. Okay. When I was looking at the individual countries, a lot of times they would have a they would have this kind of curve, and then they would go up again because they had the second outbreak, they had the second wave. Okay, but just when we're looking, see Colombia, that's not looking too bad. Okay, Argentina, we could hope. Okay, but when we're looking at you know, these kinds of curves for countries, right? If you know, this is every pet, every disease, every population of things looks like this. Okay, so if you see the population and it's a disease and you're still here, you've got a long way to go. You really, you envy those people. Okay, because this country is kind of, you know, these people would have it kind of under control. Okay? I mean, you're still getting more people, but the cumulative amount is not, you're not rising on a daily basis here. So this is kind of what you're hoping for. Okay, I don't know if I can look at New Mexico. That would be nice. We used to be able to. I don't know. I should have checked that before I started with all of this. It was data table. Anyway, I went to the Johns Hopkins site and eventually it brought me here. So I'm going to guess that the WHO coronavirus disease dashboard, the World Health Organization, it seems to be a pretty reliable thing. Cumulative cases, again, this is the curve that we're talking about for all of this. And if we look at something like, I think I looked at Turkey before. No, not Turkey. Turkey's terrible. I liked South Korea did really well at the beginning, and then I have to find Republic of South Korea. I know it's on here. There it is. See, South Korea. The timeline is terrible for this, but South Korea. I remember looking at them at the beginning and thinking, "Oh, they've got this." No, they don't. And then no, we don't. Okay, so that's your cases. These are your deaths. Okay, these are dailies. Okay, so if I took an average rate of change between these two, that would be these little spikes here. Okay, that's what the average rate of change is going to tell us there. But yeah, did pretty well, and then they had another outbreak, so not so good. Okay, again, they're starting to curve over. And back to the United States here. Top. Going, come on. Yeah. So again, we're starting to curve over here. Hopefully we don't get another, you know, it doesn't jack up like it did for Korea like that again. So we kind of starting here, and I was kind of hoping, and then no, November, no. So mathematically, right? That's how we're looking. That's how I see this thing. So that's kind of what we're looking at. All right, let's go back to something mundane. Let me see here. Not this one. Oh, we can talk. Okay, here we go. So epidemics of cholera. It's always a fun thing to deal with. So yeah, this was. I think this was the epidemic that gave people the hint it gave physicians the hint that cholera was spread by drinking contaminated water. And because, yeah, they narrowed it down to one pump in the city and got from there. Okay. So the cumulative number of fatalities, okay, T days after August 31st is given by, boom, there we go. I'm sorry, all of these are, almost all of my examples here are kind of morbid. I'm sorry. I had an office mate who had she did her project on something that uses the Donner Party to model it. So for 2 years of her life, all she got to do was read about the Donner Party. So, all right, cumulative number of deaths given T days after. Okay, determine the cumulative number of deaths by September 15th. Well, how many days? I tried to make this easy. How many days after August 31st is September 15th? And that's going to be 15 days. Okay. So and I don't know if our book has this problem. I think it does, because I think that's where I stole it from. I don't know if it was, I don't think it was given to you as homework, but it was in our book. Okay, so there's our deaths by time. Determine the cumulative number of deaths. That's what this is, right? This cumulative number of deaths T days after. So the cumulative number of deaths on day 15. So we're going to set T is equal to 15, round to the nearest whole person. Okay. So what we're going to do is we're going to say D, right? So how many people died? 91 plus 160. And now we're going to put in 15 plus 1. That's really all there is to this problem. Okay, so I know this one was kind of weird to look at, but oh, what happened to the natural log? ln of 15 plus 1, 16. Okay. Mistakes that people made on this one was mostly dealing with this 15 plus 1 and trying to break it apart. But for the most part, part A was pretty tame. I think almost everybody gets part A correct, assuming they've done the intro homework. It's not always a good assumption. Okay, and then round to the nearest whole person. This was 534.6. We'll call it 535. Okay, 535 people had died in 15 days here. Okay, when did it reach 600? So now we're going to say 600 is equal to 91 plus 160 natural log, and then I don't know what day it's going to be. All right. So subtract 91 from both sides. 600 minus 90 is 510. So this is going to be 509. That is equal to 1600, or no, 160 natural log t plus 1. We still have to get this out, right? So we're still going to divide by 160, divide by 160. And then we're going to say, well, what's 509 divided by 160? 509 divided by 160. Okay, so this was 3.18125. That is equal to natural log of t plus 1. How do you get a variable out of a natural log? Well, how do we get the variable down from the exponent? We took a natural log. So in order to get rid of the natural log, we have to make both sides the same base. We have to make them exponent to the same base. Okay, so this bit here is just going to come back with a t plus 1, it equals 2. And then it's just going to be e to the 3.1718125 here. It's going to be like 70-ish. Okay, and then the next thing we're going to do is we're just going to subtract 1 from it. This is 18125 minus 1, and that's our t. All right. So let's see here. we wanted the, okay, so this is going to be second function ln, okay, 3.18125, and the parentheses, because I don't want to do anything more on the exponent, okay, so we could either equals and then -1. I think -1 will do it up here as well, but let's be safe and hit equals, and then we'll subtract -1. Okay, so T was in about 23 days. So September 23rd is when we had our total death count here. All right. So that's a logarithmic equation. These are not actually too common that we ask you guys to solve these. Algebraically, yes, but word problems, exponentials are a little bit more common than logarithmic. Okay. Let me do one more. Let's do a biology one. Okay, so we're going to do a P is equal to P sub 0 e to the kt. Let's say that, let's say on June 1st, biology department counted 1,000 mosquitoes in a certain area. And 1 month later, they counted. And what they do is they go in an area and they sample the number they have, and then they make an estimate. They don't, try to pinpoint every mosquito to count them. Okay. Let's say they counted, and we'll say 2,500 mosquitoes. When will there be 4,000 mosquitoes? And clearly, right, we're going to have to be kind of careful about this because if we end up with 6 months, there's not going to be 4,000 mosquitoes in December. Okay, so I'm hoping that at worst I'm going to have something in September here. Okay, so I should have been more careful about setting my date. Maybe I should have said May and done this. Actually, let's do that. Let's go with May. May, there's 1,000 mosquitoes, and then 1 month later, there's 2,500, and then when will there be 4,000? Okay, it's kind of like people who look at a graph and like, oh, Christmas sales were really up in November and December. I'll bet we'll have a great month in January. Well, all right, so what we're going to do is we're going to use our formula here. Okay, and we're going to say our P sub 0, right, was 1,000. And then 1 month later, okay, so I'm giving you a time frame. Okay, so T is equal to 1. K, we don't know. We don't know what the growth rate is. But 1 month later, we know that P of T, right, the left-hand side, that's 2,500. So let's set this up. We have P equals P0 e to the kt. So we have 2,500 here. Excuse me, equals 1,000 over here. E to the K, I don't know. And then 1 month. Okay, so our K is going to be in months. Okay, our growth rate is going to be in months here. So we're just going to say 2,500 over 1,000 is equal to e to the K. So that's nice. That's going to be 2.5, right? 25 over 10 is 2.5. Is equal to e to the K. Take the natural log of both sides. We have K times the natural log of E, which is 1, equal to the natural log of 2.5. So we can just put this over here, and K sub m for mosquitoes is equal to the natural log of 2.5. Okay. Next, so well, how long is it going to take, right, to have 4,000? So we're going to say Well, we have P is equal to P sub 0, e to the K, which I know we have K sub m times T. So we're going to have 4,000 here equals, how many do I start with? 1,000. E to the K sub m times T. We're solving for T. Okay, so let's go ahead and divide by 1,000. Okay. This is also really good final exam problem because all the numbers are very nice, right? So no decimals, no extra stuff in here. So we have natural log of 4 is equal to the natural log of e to the K sub m times T. This bit comes down in front. Okay, natural log of e, which we know is 0, or 1 rather, natural log of 4, ln. Okay, so t, right, is equal to the natural log of 4 over what k is, and k was the natural log of 2.5. Now remember, this is a formula. It's called change of base formula. It is not the division formula. Okay, the division formula says natural log of a over b is equal to the natural log of a minus the natural log of b. Only one natural log on that side. So don't look at this and say, oh, I can take that and subtract. Like, no, you can't. You got to divide this. Or what you can do is say, well, this is the log base 2.5 of 4. I'm sure that that's not going to be a fun thing to figure out. So we're just going to do it this way. Okay. So we're going to say natural log of 4. I'm just saying, I've seen students do this before, trying to be clever. And I applaud you for being clever. That's good. You should always try to be clever. But in this case, you stabbed yourself. Don't. You misinterpreted that. So t was equal to about 1.5. June would have been safe, okay, because that would have been halfway through July. So 1.5 months from that would have been halfway through June. Okay, so June 15th. There we go. That's when you have 4,000 mosquitoes in that area, and get your mosquito spray. Order enough mosquito spray to deal with it accordingly. Okay. I think that's good for today then. Okay, so I'm going to go ahead and stop our recording. So good luck with everything with that. I might try to do something for you guys next week. It's a little bit different, and we'll see. All right.